Thank you. I'm actually very excited to be here today speaking in Belgium because Belgium is a very special place in my life. It turns out that many years ago, I went to middle school here in Belgium in a small university town, half-hour drive from here, called Louvain-la-Neuve. And so when Databricks invited me to give this talk, I was very grateful and excited to do it. And when we were looking at some of our old pictures from Belgium, it turns out we took a picture in this garden right behind the building. So I thought I'll share that with you. Many years ago, right? And so this is going to be the only technical diagram in the whole talk. Okay. All right. So back to the talk. Digital advertising is a huge business. In display marketing alone, marketers are spending at least $25 billion a year. And MediaMath is one of the leading software platforms for digital display advertising. We have thousands of advertisers who've set up tens of thousands of ad campaigns on our platform, and we bid on their behalf on the ad exchanges. We listen to over 40 different ad exchanges, and we receive over 200 billion ad opportunities every day, which translates to around 2 to 3 million a second. And in response to each of these bid opportunities, our bidding systems respond within 10 milliseconds with two optimal decisions. One of them is the optimal campaign to bid for, and the other is the best bid price to submit to the ad exchange. All of these optimizations are driven by massive amounts of data. So 200 billion opportunities a day. We track over 1 billion user cookies. We have data ranging from impressions to clicks to page visits, conversions, and so forth. And each data point is very rich in terms of features. The number of dimensions could be in the tens of millions, highly sparse features. So all of this translates into several terabytes of data per day. And we rely heavily on Spark for several of our large-scale data applications at MediaMath. So over the next several slides, I'm going to go over into a little bit of depth on 3 of these applications and briefly mention 3 others. Okay? The first one is a core application for our business, which is predicting the response to an ad from a user, right? So what is the probability that a user will respond to an ad or will have a conversion? When I say conversion, I mean any desired behavior that the advertiser cares about. It could be a subscription, it could be a purchase, it could be a click, or anything else that's important to the advertiser for the ad campaign. Predicting this probability is important because it's a crucial component that informs the bidding price decision. The higher this probability is, the more valuable this impression is to the advertiser, and therefore the higher they should be willing to bid in the ad exchange. Okay? So we trained several machine learning models, one for each campaign, and we use logistic regression as a model and stochastic gradient descent algorithms, which allow us to do incremental updates. And all of this is implemented in Scala and Spark. So in addition to training these models, we in particular use the Databricks platform to visualize the performance of these models across several campaigns, model variations, and machine learning metrics. Here's an example of a visualization. So you see 4 big columns here. Each big column is a different machine learning metric. You have AUC, you have relative information gain, and several others, and a couple of others. Each metric has its own color. Each row is a campaign. And within each big column, you have 4 thinner columns. Each of those is a model variation. So we're able to see multiple campaigns, model variations, and metrics in the same visualization. So this allows us to see at a glance if there are any models that are dominating all the others across all campaigns, Or maybe there are some models that do better on certain kinds of campaigns than others. Okay, the second problem is the problem of measuring the causal effect of advertising. By that I mean how much of a response of a user to an ad is driven purely by the ad exposure. So let me explain. Let's say an advertiser finds that 5% of users exposed to their ad buy their product. What they would love to know, though, is that entire 5% due to the ad itself, or perhaps without the ad exposure, maybe 4% would have bought anyway without the exposure. So the incremental response because of the ad is just 1%. And that incremental response is very important to measure for an advertiser because it tells them how effective is the advertising in driving response. So several of our clients want to measure this. So this is actually a very tricky problem in general. But the high-level idea is relatively simple. Okay? So we do a randomized test. We split users randomly into test and control and submit a bid only for the test users. Now, if you do this naively, there will be several subtle statistical bias issues. And we are one of the first in the industry to come up with a methodology to account for this bias and correct for it and estimate the causal effectiveness of the ad. In addition, we use Gibbs sampling to estimate confidence intervals around this measure. And all of this runs in production in Scala and Spark. And we report the numbers that we get out of these jobs to our clients who are measuring their ads. The third problem is audience reach estimation. The question here is, given a collection of targeting specifications or targeting criteria, a client or an advertiser wants to know how many unique users can they reach with these criteria. So here's an example of a targeting specification for an ad campaign. Each row here is a feature-value combination. So the feature segment has value sports, the feature country has value Belgium, day of week has value Sunday, and so on. So think of each feature value as defining a set of unique users that satisfy that feature value, right? But the advertiser wants to know how many unique users satisfy all of these feature value combinations. So, in other words, this is a set intersection cardinality problem. And the scale of this problem is big. The incoming bid ops are the source of our data. We track over 1 billion user cookies. And the constraint here is that we need the answer in under a minute. We cannot afford to run a large-scale query in real time and wait a half hour for the answer, right? And also, on the other hand, we cannot pre-compute the answer for all possible queries. Like I said, the number of possible feature values can run into the millions, okay? So in other words, there are 1 million different possible sets that they can query about. In a given query, there might be 10 or 15 or 20 of these sets, right? We cannot anticipate all possible combinations of these sets and pre-compute the answer to those. So our solution is a two-phase solution. There's an offline phase where we use a combination of Spark and Redis to store k-min hash sketches for each of the individual feature value combinations. And then there's an online phase, which at query time, in a given query, there will be about 10 or 15 of these sets that are specified, and to compute their intersection, we retrieve the k-min hash sketches for these individual feature values that are in the query, and then very quickly compute an intersection of these. So 3 other applications I want to mention very briefly here. First one is attributing clicks and conversions back to the impressions that led to them, which is very important if we want to have accurate machine learning models and accurate estimates of ad effectiveness. The second one is predicting the probability of winning an auction at a certain bid price. This, in addition to the machine learning input that I mentioned before, where we want to predict the response of a user to an ad, Both of these are crucial inputs to the optimal bidding decision. And the third one is tracking human users across cookie and device changes. Because we only see cookies in our bid opportunities. We do not see the identity of the actual user. However, as users move from device to device, or they refresh their cookies, their IDs and cookies and device IDs change. So it's crucial for us to be able to link multiple different cookie IDs or device IDs as belonging to the same human user. And you can imagine why this is very important for better targeting, as well as for better machine learning predictions and accurate ad effectiveness metrics. So now I want to turn my attention for the rest of the talk to the Databricks platform itself. So in the 6 months since we've signed on to Databricks, it has become an indispensable platform for data science productivity. So in the next several slides, I'm going to talk about how we use the platform and what we love about it. Of course, we can do very quick ad hoc data analyses on our data in the notebook environment in several languages. So as a result, we have, across our users, we have hundreds of notebooks in different languages, and these are elegant and responsive environments to work with. We also have hundreds of tables that help us easily access our most important data sets. It's very easy to spin up clusters, unlike, say, going to the AWS console and firing up a cluster there. And it's particularly easy to run a jar, to run a job. Let's say you wrote a Scala job and you compiled it. I used to use shell scripts with Spark Submit to do this before Databricks. But with Databricks, it's very easy. You just import the class, set up the arguments, and then call the main method on that class with those arguments. Of course, you can run notebooks as jobs and schedule them, which we do a lot. And we often create and share dashboards of results, both within the team and outside the team. And we exploit data visualizations in several of our projects. And one of the nicest things about the platform is that it's a fantastic learning tool. There are several helpful tutorials, example notebooks. So for anyone trying to get up to speed with Spark or even machine learning and data science concepts, it's a fantastic environment. In particular, for people who are joining the data science team, this has proved to be a very useful environment to work with. And finally, I'll close by saying the platform makes it very easy for us to run projects with our external collaborators. For example, we are affiliates of the Data Science Institute at Columbia University. And so as a part of that, every semester we run a capstone project, which involves making some data accessible to the students and having them work on a certain project. With this platform, this is very easy to do. We set up an account for the students and give them access to the data, and they can start working on it right away. And so that's all I have. Thank you very much.